Hello everyone, welcome to the YouTube channel E for EMF. This is a control system series of our channel. In this particular video, we will learn how to draw a Nyquist plot for a type 0 system, in particular example number 1. So what is Nyquist plot? It's a frequency response technique which shows us the behavior of open loop system with respect to changing frequency, and that same behavior tell us the stability of closed loop system. So in short, from the open loop transfer function, you can tell the stability of closed loop transfer function. To understand this concept in more detail, please watch the video whose link is given in the description box below. So the Nyquist plot can be plotted for different types of system. So type 0 system, it's a system or a transfer function who has no pole at origin. So here there are two poles, P1 at -1 and P2 at -2. But there is no pole P3 at origin. That's why this is a type 0 system. Type 1 system is a system who has one pole at origin. Here we can see that. And type 2 is a system who has two pole at origin. So to understand type 1 and type 2 problems, we will create two more videos. But in this particular video, we'll understand how to draw a Nyquist plot for type 0 system. So a unit feedback system is given to you whose loop transfer function g of s is 50 upon s plus 1 and s plus 2. Here unity feedback is there, that means h of s is particularly 1. So whenever you want to draw a Nyquist plot, you have to draw it for a transfer function, a loop transfer function g of s h of s. Here h of s is equal to 1, hence the loop transfer function g of s will remains as a g of s. So how this Nyquist plot is drawn? So it's basically a mapping of S plane to particular W plane whose real axis is at sigma and imaginary axis at j omega. So how we define the stability of any system? We see if there is a pole at a right hand side of the S plane. So if there is any pole at the right hand side of S plane, the system will become unstable. So what if there is a technique which maps entire right hand side? This particular technique is called Nyquist plot. So with this we draw this Nyquist plot by mapping entire right hand plane starting from the origin, and we will go towards positive imaginary axis, that is where omega varies from 0 to infinity, right? So this particular part, let's name it as a part 1. So part 1 where omega varies from 0 to infinity. Then the part 2 is covered, which is a semicircle in the entire right hand plane, and which is having some radius. Let's name this radius as r e raised to j theta. So the part 2 is mapping entire right hand in the form of semicircle. So the part in the part 2, it's r e raised to j theta, where r tends to infinity and theta varies from plus 90 degree to minus 90 degree. Then the third part, which is mapping this particular part 3. In part 3, if you can see, omega is varying from minus infinity to 0, right? And this is part. So apart from part 1, part 2 and part 3, there is one more part 4, which is a very small semicircle near the origin. So the part 4 comes for particularly type 1 and type 2 system, where there is a one or multiple poles present at origin. If there is no pole present at origin, then this part 4 will will not be there in our Nyquist plot. But for part 4, it's basically a semicircle which is having radius r e raised to j theta, where r is very small, it literally tends to 0, and theta is basically varies from minus 90 degree to plus 90 degree. So if you want to see, this is 0 degree, this is minus 90 degree, this is minus 180 degree, and this is minus 270 degree, or either this can be a 90 degree and this can be plus 180 degree, and this can be plus 270 degree. So the part 1 goes from origin towards infinity, where omega is varying from 0 to infinity. Part 2 is coming from infinity and mapping entire right hand plane with radius r e raised to j theta, where r is is nearly infinity and theta is going from plus 90 degree to minus 90 degree. The third part is coming from infinity towards origin, and that is where omega is varying from minus infinity to 0. And the fourth part, particularly, this part is very small. It is only present for a system having pole at origin, and its radius is r e raised to j theta, where the small r is very negligible. It's nearly equal to 0, and the angle which is taking by it is minus 90 degree to plus 90 degree. So how to, by mapping this entire right hand plane, we can draw a Nyquist plot which can look like this or anything like this. So this can be drawn by mapping this four parts to some omega to some w plane. This plot can be drawn by mapping this entire S plane to some W plane by using some steps. So what is the first step? We need to draw the first part 1. So in the first step, we will put S is equal to j omega. So this transfer function will then become g of j omega is equal to 50 upon j omega plus 1 j omega plus 2. So we need to map this thing to some w plane which is having some magnitude and some phase. So this magnitude of this transfer function is calculated. Magnitude of say, this transfer function j omega can be calculated by using a very basic rule, that is, if a complex number is there, e plus bj, its magnitude is calculated by taking square root and adding it, a square plus b square, right? So this is how we calculate this. So for 50, for numerator 50, there is no complex part, so it's basically square of 50, and denominator square root of real part square, that is 1 square, plus imaginary part square, that is omega square. For second number j omega plus 2, we take a square of real part square, that is 2 square, and imaginary part square, that is omega square. So I can write this 2 square as 4. Similarly, I can calculate phase of this transfer function g of j omega. So a complex number a plus bj, its phase is calculated by tan inverse of b by a. So its complex number is nothing but a vector quantity, and we are putting it into a polar form. So similarly, this can be calculated as tan inverse of numerator, that is real imaginary part of numerator, that is 0, divided by real part, that is 50. So division in complex domain can be addition in or subtraction in polar form. Tan inverse 50. So the denominator, we can take a minus sign, that is minus tan inverse of imaginary part omega upon real part minus tan inverse imaginary part w upon real part, that is 2. So tan inverse of 0 by 50, that is tan inverse of 50, it is again equal to 0. So I can write this as minus tan inverse. So this particular part will vanish to 0, and we will left with tan inverse of omega minus tan inverse of omega by 2. So now we do have two equations. Equation number 1, which is magnitude of the mapping path, and equation number 2, which is phase of this. So I can, so what we want to draw, or what we want to vary this omega part for part 1 and from 0 to infinity, and we to plot this magnitude and phase of this particular. So let's calculate this magnitude and phase with respect to changing omega. So let's say I want to draw 4 to 7 points, and I want to vary omega from 0 to infinity, and let's take a middle value, that 0 1 2, let's say 10 20 100 infinity. So when I put omega is equal to 0 in equation number 1, I'll get a magnitude, that is 50 upon square root of 1 into square root of 4, that is 50 by 2, that is I'll get 25. And when I put omega is equal to 0 in equation number 2, here tan inverse of 0, that is 0, minus tan inverse of omega by 2, that is 0 by 2, again 0. So what I'll get, that phase is equal to 0 degree. So when I put omega equal to 1 in equation number 1, I will get a magnitude as 16 and phase at minus 72 degree. When I put omega equal to 2, I will get magnitude at 8 and angle at 108 degree. Similarly for 10, I will get 0.5 and angle minus 163 degree. For 20, 0.1 angle minus 171 degree. For 400, I will get 0.005 as a magnitude and angle at minus 178 degree. And for infinity, if I put infinity in magnitude here, so I'll get 0 because denominator will be 0, and tan inverse of infinity is 90 degree minus 90 degree minus tan inverse of infinity by 2, that is infinity. So I'll get minus 90, that is minus 180 degree. So for every omega I'll get magnitude and phase. So if I plot this magnitude in phase, I will get first part of Nyquist plot. So how to plot it? Let's take a graph paper, and we know there is maximum value of magnitude is 25. So let's take a unit of 5. Okay, so the first point for omega is equal to 0, magnitude at 25, and phase is 0. So this particular point, we first need to take an angle, that is 0 degree here, and then angle will, if you measure angle in anti-clockwise direction, then this point is in negative real axis will be at minus 90 degree. This negative real axis will be at minus 180 degree, and this is at minus 270 degree. So for omega is equal to 0, what I will get is the first point, that is omega is equal to 0. I'll get first point, this one, at 25 and angle 0 degree. So second point, omega is equal to 1, I'll get magnitude 60 at angle minus 72 degrees Celsius. So minus 72 degree will come somewhere around here. So let's say this is minus 72 degrees Celsius. So I'll get magnitude at 60. So this will be the second point with omega equal to 1. Next point is omega equal to 2, the magnitude is 8 and phase is 108 degree. So 108 is will come somewhere here. Say this is minus 108 degrees Celsius and the magnitude is 8 somewhere here at omega equal to 2. Now the next point, omega equal to 10, I have magnitude 0.5 and angle 163 degree. So the angle 163 will come somewhere here. And mm, that value is 0.5, omega equal to 10. Next value will come at minus 171 degree. Let's say this is here. And the last will come at minus 178 degree. That is somewhere here, minus 178 degree. So at 171 degree, I have magnitude 0.1 and omega 20. Yes. Omega equal to 20. And the last part is magnitude 0.005 somewhere here and at omega equal to 100. And at last, the omega is when the omega is infinity, the magnitude is 0 and angle at minus 180 degrees Celsius. So I will get the angle is 180 degrees Celsius is here, but the magnitude is 0, so the point will come somewhere here. So if we join all this point, I will get first part of Nyquist plot. So omega is varying from 0, then it's 0.1. So the graph will go, the Nyquist plot will go in this direction. This let's is at omega equal to 10. Okay, the first part is done. That is, we vary omega from 0 to infinity plus infinity, and we plotted magnitude and phase of this particular part. Now the second part is where this semicircle is to be mapped. This entire semicircle which is having radius, this particular part. So let's draw the second part 2, where there is a semicircle of a radius r e raised to j theta. So in this case, the r is tending towards infinity. So and theta is varying from plus 90 degree to minus 90 degree. So in this case, we put s is equal to limit r tends to infinity r e raised to j theta in our transfer function. So the transfer function will become g of r e raised to j theta is equal to 50 upon limit r tends to infinity r e raised to j theta plus 1 r e raised to j theta plus 2. So if we rearrange this equation, I will get 50 upon 2 r e raised to j theta common. So if we rearrange this equation, we will get 50 upon limit r tends to infinity r square e raised to 2j theta bracket 1 plus 1 upon r e raised to j theta plus into 1 plus 1 upon 2r e raised to j e raised to j theta. So if we put r is equal to infinity in this term, if we apply the limit, then this term will vanish to 0 and we will left with 1 upon we will left with 25 upon r square into e raised to 2 times j theta. So this particular part will be our magnitude and this particular part will be our direction, that is angle. This particular part is phi. So m will remain 0 for this part and this direction phi will be e raised to 2 times j theta, where theta varies from plus 90 degree to minus 90 degree. So e raised to 2j theta, theta is varying from 90 to minus 90. So this phi will vary from minus 180 degree to plus 180 degree. So there will be a circle of magnitude 0. That circle will vary anti-clockwise direction from minus 180 degree to 180 degree and for part 2. So the graph in this part, let me draw it with blue color, will start at minus 180 degree Celsius. A small circle will be there in anti-clockwise direction and it will end up here. So for this part, the magnitude of this radius of this circle, that's going from minus 180 degree to plus 180 degree, that means it is taking entire one circle, its radius will be equal to 0. Okay, now the third part is nothing but omega is varying from minus 90 degrees Celsius to plus 0. So this is exactly a replica of omega varying from 0 to minus 90 degrees Celsius. So we can draw this replica of part 1. So the part 3 will be exact replica of part 1. So let's draw. So this exact replica will start from this 0 and end at this point. So this is graph for part 1. This is part for part 2 and this is for part 3. Okay, so the part 4 is a semicircle of radius r e raised to j theta. But this semicircle is missing when there is no pole at origin. Therefore, as there is no pole at origin, hence part 4 is not there in Nyquist. Okay, so the part 4 will not be there as there is no pole at origin. Stability can be derived by using equation n is equal to p minus z, or if we rearrange this equation, z equal to p minus n. So what are z? Z is poles of closed loop system, p is poles of open loop system, and n is number of encirclements. So here n is equal to number of encirclements of Nyquist plot to -1 plus j 0. So how many encirclements are there to this point is the value of n, and let's see what is the value of n in this graph. So in the graph we have drawn here is the part is -1 point is somewhere here, because this entire angle at angle -178 degree, the value is 0.05. So -1 will be somewhere around here, -1 plus j0 is here. So there is no encirclement clockwise or anti-clockwise encirclement to -1 and 0. So the value of n is 0 for this. So what is the value of p? P are the poles of open loop system which are in right hand plane. So our transfer function is here, and both the poles are on left hand side. So there is no pole on right hand side. That means the value of p is again 0. So the value of z, that is p minus n, that is 0 minus 0 equal to 0. So poles of closed loop system are 0. Closed loop system in the right hand side of S plane is equal to 0. That means the open loop system, as there are no pole in the right hand side, that means the open loop system is stable. And as Z is equal to 0, the closed loop system is stable. So if any value z is equal to 1 or z is equal to 2, if there is if by calculation or by graph, if z becomes 1, then there is one pole on the right hand side of the closed loop system, and we know if there is any pole on the right hand side of the closed loop system, the system will become unstable. So in this particular case, z is 0. That means there is no pole on the right hand side of a closed loop system, and hence the closed loop system is stable. So this is how we draw a Nyquist plot for type 0 system. Thank you everyone. Please like, share and subscribe to our channel. Thank you.